Now, what we're going to do, we're going to use the method of random forest. And random forest is having a very good reputation in getting a good results for in general in machine learning, and so we will use it now. So first, as we did before, let's understand how the random forest works. The way the random forest work is by having many decision trees. So what is a decision tree? A decision tree is a way to classify our data using the features of our data. So we will have many features. For example, in our case, in the engines situation, we have for example, the temperature or LPT temperature should be if it's more than this or less than this. If the EGT, the engine gas temperature, become more higher than this value, we can classify it as this, or so on. So these indicators, these features we can use it to classify our data in case of classification problem, and in case of regression problem we can give it values. So for example, if we have the first feature to be, if it's true, it will get us into another check of features, and if it's, for example, yes, we will go to a specific value, and if not, it will go for another decision tree or branch, and then we will go to other values. So this is how the regression works. Of course, in classification, it will send us to classes. So this is going to be class 1, this is going to be class 2, and so on. So we're using features to build branches that will direct our data to specific classes, and in case of regression, to specific numbers. Now, so what is this is decision tree. This is just decision tree. Now, the random forest, as we said, it is a combination of decision trees. It's a lot of decision trees, and these decision trees going to vote. So in case of classification problem, the decision tree is going to vote which class belongs to which the data to which class it will belong. So every tree will have one vote, and because we have many trees, these trees we're going to have many votes, and based on that we will take the final answer. Now the problem is, how do you build these trees? Well, we use to build these trees, we use different features. Not all trees has to be the same. This is why we call random forest. It's a random of decision trees, or these decision trees we call it as forest. So the name came random forest. These trees going to be made from different parts of the data, and these trees are made from different features. So the combination is random, and we have a lot of trees, sometimes 300, 400, maybe 1000, and these trees have different even depth. So the depth is how much branches we go, as you can see here. In this case, we have only 3. So this is how we create many trees, and at the end, these random trees are going to vote. Some of them will vote not correct, but and collectively it will vote correctly. So we have, of course, hyperparameters in relation to these trees. Of course, in scikit-learn, we can assign the hyperparameters we want, but also you have to understand that scikit-learn has the random forest and many other methods have many hyperparameters. You have to go through the documentation and to find it. But however, the most general parameters can be number of estimators, which is basically the number of trees, how many decision trees we have. In what we will put in here 300. Maximum or max features. Now how many features we will take, and it's called a square root. So the square root means the number of feature we will construct these trees is the square root of the number of features we have. So if we have, in our case, in our engines, we have I think 18 or 17 features, so that will be the square root of 17 is going to be the number. Of course we have to make it integer, is going to be the number of features that we construct these trees. Maximum depth is the maximum depth of the trees, and random state is just a random state. Is like when you're doing a random generator, you can put it anything. Like here we have it 18, but you can, really doesn't matter. You can put it 25, you can put it 2525, it doesn't matter. So just to code our method, we again do the same thing, basically import the library, and then import the solver from that library, and then we just fit the model and then predict the test and compare it to find the root mean square, in our case the error metric. So again, from sklearn dot ensemble import random forest regressor, and of course the random forest, every forest will for the regression itself, we took the voting, so every tree will predict the value, and the final will be the average of these like voting. So from sklearn ensemble import random forest, and here we do the same thing, which is we call we start the time, we call the model to be fitted, and here so random, and then prediction, and so on. Random forest, just take it from here, in estimate and estimators equals 500, max features is your square root, max depth equals 5, and random state equals, in our case, we said 18 or something. You just do it, write anything you want. I'll write just 25. So here the fitting of the model, prediction, and calculation of the time. So we run it, and we just, let's copy and paste these graphs. Of course you can graph anything you want, and we take the other graph, right? So here we can see the calculation is quite reasonable. 8 seconds. The root mean square error reduced significantly. I think the lowest we got from the nearest neighbor is 580, so now 481, and the prediction is become more towards the line itself, a little bit less spread, especially here. So if the line, as the best way we have is this line, if we predict 50, it will have the exactly 50. Let's say, of course, this line is just to show this tendency of this line from these points as a curve fitting, but in actual case, the 100 here, if it's actual 100, the predicted should be 100. So it's better to have this to be basically actual is exactly what we predicted. In general, here is good, here is not so good in this case. Now we can see here the actual and predicted. In this place is quite reasonable for these number of engines, but the small number of engines, the engine numbers, have a low value. So I think these numbers of engines has an remaining useful life is a little bit higher than these engines, because or when the engines have a higher remaining useful life, we're getting a bad result. So you can see here in the random forest, in the RUL, the remaining useful life, if it's small, the as small as possible, the prediction will be as more accurate. As we go for a higher RUL, which is reasonable, we will have less predictability, less powerful prediction. The engines, of course, this is engine number, this is not RUL. In the engine from 0 to 20, we have a bad performance. But here, these numbers of engines, I think it has according to the data, it seems to have a little bit lower remaining useful life, and it is very, as I said, it's very logical.